slide? Okay. Okay, thank you.
Okay.
Thank you, Maria. Okay, sorry for that. So as I was saying, this work was done in collaboration with Igor and Alexei, and the funding was provided by NSF and the computational resources by Exceed and Frontera supercomputer at the TAC. Sorry, this is not working to change the slide. Arrow down. Okay, thank you. So our goal in this work was to investigate promising layer superconducting materials in the lithium magnesium boron system, and in numerous studies and also in a few talks at this conference has been highlighted the importance of coupling careful structure prediction with accurate superconductivity analysis. So in my talk today, I'm also going to discuss both aspects as well. So I will start the presentation by overviewing the extensive work done on the lithium boron superconductors, from its prediction and synthesis to first superconductivity analysis that were performed, and then I will describe our revisiting of the system with the Migdal-Eliashberg formulas to get a more reliable estimate of the critical temperature. And in the final, in the second part of my talk, at the end, I will describe our work on related MGB2 type superconductors. So as I will say, as I will show, all the materials that we found in these systems are metastable, but I think the important investigating their superconducting properties help establish the importance of anisotropy in these layered systems. So as I said, there's been extensive work done on the lithium boron system, and the first investigation was done in 2006 when the material was predicted to form. However, really finding or predicting the conditions, let's say the experimental condition in which the compound can be synthesized, proved to be quite challenging, because the starting, there was no reliable model for the starting material, lithium BX, near the 1,1 composition. So once this material was modeled with variable unit cells of lithium boron chains where the lithium and boron ratio of the atoms was varied, it was found that lithium boron should form at about 10 gigapascals. A few years later, Lazicki and collaborators performed a high pressure experiment, but they don't find any evidence of the formation of the lithium boron stoichiometric compound up to 70 gigapascal. So this kind of came as a surprise, because I was aware at the same time of the experiments done by Alexei's team that have found the first evidence of the existence of the formation of lithium boron. However, it took a few more rounds of experiments and also a lot more modeling work to conclusively show that lithium boron indeed formed, and they were also able to anneal the sample down to ambient pressure. So that work was published much later in 2015, but as you can see, it basically took about 6 years to really figure out and synthesize this material. I'm not going to go into many more details about the synthesis, because Alexei is going to give some more detailed information in his talk tomorrow, and also describe a new proposed route to synthesize this compound at a much lower pressure. So now I'm just going to move and discuss the superconducting properties. And as I said, this is a review. This was described in detail in a couple of publications. So by Matteo, Alexei, and Stefano. And at the same time, Enliu and Igor Mazin have also been investigated ab initio the same system in 2007. So here I just want to overview some of the key electronic structure features that were pointed out in these original studies. And what was found is that as lithium boron is even more two-dimensional than MgB2, and in fact has a higher density of states provided by the boron sigma states. But on the other hand, it has negligible contribution for the boron pi states. On the other hand, in lithium boron, as you can see here, there is some density of states that comes from the lithium nearly free electron bands. And this is reminiscent of what's happened in calcium intercalated graphite. So despite these promising electronic features, it was estimated based on the Macmillan expression with the isotropic Eliashberg spectral function computed with quantum espresso that the TC should fall in between 10, 15 Kelvin. So as I said, the goal of our work here was to investigate lithium Ng promising superconducting materials from in the lithium magnesium boron. So within this work, we also decided to reinvestigate the lithium boron superconductor just to have the same the analysis done at the same level. So before I'm going into showing our calculation, I just want to give you just a brief overview of how we perform the our superconductivity calculation. So I'm using the EPW code, which is an open source code that comes with the quantum espresso package. And I would say the strength of EPW is that it couples the density functional perturbation theory, the strength of density functional perturbation theory with maximally localized Wannier functions. So this allows accurate calculation of electron-phonon interactions. So in other words, electron-phonon matrix elements, starting from coarse grids calculated with quantum espresso, then using the Wannier interpolation technique by calling the Wannier 90 code as a library, and then obtaining the electron-phonon matrix elements in the real space. And then you can go back on the fine mesh, basically using any mesh that you can afford. Once you have electron-phonon matrix elements, you can calculate a number of properties with EPW, among which you can solve the anisotropic Migdal-Eliashberg equation. So in this case, these are the two equations in what is called, right now a few papers have referred to this as the Fermi surface restricted, because these two equations are obtained under the assumption that the superconducting, the pairing mechanism takes place within a small Fermi or small window around the Fermi surface, and the density of states at the Fermi level is assumed to be constant. We have currently, in the current version of the code, they have also went further and have also implemented the full bandwidth description, but that has not been used in this study. So one limitation that I should point out in EPW is that we are still using a semi-empirical parameter for mu star. In a number of studies, we have calculated this by using the spin Coulomb interaction with Sternheimer GW. In fact, Christoph has done quite a number of studies, I think, in hydride disease. And I know that Antonio has done a lot of calculation recently of estimating mu star ab initio and for most systems, when for phonon-mediated superconductors, mu star falls within the 0.1, 0.2 range. So now let me go back to our calculations. So here I'm just showing a comparison with magnesium diboride. So in agreement with the previous studies, the previous ab initio studies, we found that the coupling with the boron-boron stretching E2G mode is reduced in lithium boron compared to MgB2. So here this dot shows the strength of the electron phonon coupling. And as was pointed out by Matteo, this is due to the different dispersion character of the two bands. So you can see in MgB2, this band is largely dispersed, while in lithium boron is way more flat. On the other hand, in lithium boron, we have some coupling that comes from this very soft mode below 10 milli-electron volts. So in order to reduce, let's say, the noise or in our calculation due to the mu star, we have compared for two values, mu star 0.1 and mu star 0.2. So here I'm showing the results for mu star 0.2. But what we found is that for the isotropic case, we get very good, the same agreement that was initially predicted, that the TC will fall between 8-15 Kelvin. But when we solve the anisotropic Migdal-Eliashberg equation, we get an estimate which falls between 30-42 Kelvin. So this is a 3 order of magnitude larger than the isotropic prediction, and about 80% the estimate from of magnesium diboride. Yes. Lambda indeed is very close. Yeah, it was so I should mention all these calculations have been done right now with the pseudo dojo stringent pseudo potential from the Abinit library. So when we compare, for instance, for MgB2 with older phonons done with other pseudo potential, there are slight differences. But I don't have the plot here, but we plotted against some experimental data. And this phonon dispersion for MgB2, it's in much better agreement with experiment than previous calculations. But it's true that depending on what pseudo potential you are going to use for MgB2, you may end up with values which can vary, like 0.7 I found in the literature with older pseudo potential. So, but with this, so for the study that we've done here, for all systems we use the pseudo dojo pseudo potentials just to be consistent. So we can yes. So one thing that I point out right now, that if we solve the anisotropic equation, you can see that we get a multi-gap structure that can be associated with different parts on the Fermi surface. So the highest part comes from the mostly from the boron pi states, while the lower part from the nearly free electron states. So maybe this band resolved analysis can give an even better idea of how where the coupling comes from. So this is what we plotted here, the band resolved basically electron phonon coupling. And again, we are comparing with MgB2. So as expected, since we don't have the pi states, there is no contribution to lambda coming from the pi states. There is some minor contribution coming, at least in the decomposition, coming from the lithium states, and the dominant coupling in this case is from this sigma and NFE state. So I guess I should have mentioned here, so this is the Fermi surface and this is the cross section. So in this 3-band model, we included in the first zone basically the sigma states that are slightly coupled with the lithium states. Then in the second region, this states coming from the lithium, and then the outer part would be the pi states. One important thing in lithium boron, as I mentioned earlier, is that there is no contribution from the pi states because accidentally the Dirac cones fall exactly at the Fermi level. So, so in this original study, it was suggested that pressure and in fact also doping could move the Dirac points such that the density of states at the Fermi level coming from the pi states can be improved. And indeed, if you apply pressure, you see that there is a large variation in the density of states from both boron, pi, and sigma states up to about 5 gigapascal, after which there is almost no change in the dose. And this change in the electronic structure is directly related to basically to the change in the crystal structure of lithium boron. So basically what happens at low pressure, the lithium-lithium interlayer distance collapses rapidly, and basically the charge from the intercolumn from the lithium band is forced into the boron sigma pi states. Once this distribution is complete, there is almost no change in the density of states at the Fermi level. So so here I'm showing basically what in our calculation, what happens with indeed that you can see that the interlayer distance collapses quickly, and then there is a small increase of the in-plane boron-boron length followed by a decrease. So what we found, although in this material, the van der Waals interaction doesn't play a very important role, there is still a small shift in the pressure that describes this transition between two regimes. So in the original study, no van der Waals interaction was functional was included. So the transition pressure was found to be 5 gigapascal. If you include the van der Waals functional, you will find that the pressure point decreases to 3 GPa. So now we also looked at the superconducting properties in this system using the anisotropic Migdal-Eliashberg formulas. So here I'm just showing quickly that this is our results for the density of states. So we find similar results with Matteo's study. So the density of states from so we find that the density of states decreases, and also lambda decreases as a result of not only decreasing dose, but also losing the coupling from this low frequency mode. So at this mode has a very strong coupling at 0 gigapascal, but then basically it disappears above 5 GPa, while the higher frequency modes remain nearly constant. So as a result, the TC also drops quite drastically. So at 20 gigapascal, we estimate a TC of about 9 Kelvin for mu star 0. I think this is 0.1. So these changes are also reflected in the anisotropic gap. I'm not showing here, but I guess you can figure out from this crossing that the two-gap structure or multi-gap structure is preserved, but above 5 GPa, there is no contribution from the nearly free electron states. Then the contribution from the sigma states is really diminished. And while there is some contribution from the pi states, this still remains insignificant. So we can, as you can see from this two-band decomposition model, this most or the highest contribution to the coupling still comes from the boron sigma state. So with this, I think I will just move on to the second part of my talk, and I will describe our investigation of the lithium Mg boron system. So, so in this study, we have focused on this part of the ternary phase diagram, which is highlighted here in red. And this is because this may have stable, nearly stable compounds with in this composition. So by keeping monovalent lithium and divalent magnesium, we are ensuring that we are keeping we are basically having that the boron sigma states are whole doped. So this is one of the key features that we wanted to maintain, because this is what is known to be beneficial in MgB2 superconductors. So compared to previous study by Alexei, in this in this latest study, we have also looked at by varying basically the composition in the by mixing the composition in the at the sites of the let's say of the intercallant, basically by mixing lithium and magnesium. And these are the proposed lithium magnesium boron morphologies. And we have performed thermodynamic stability analysis at high temperature and pressure. And we found that all these systems are metastable and unlikely to be synthesized with a standard bulk synthesis method. On the other hand, being layered materials, it may be worth investigating the possibility of synthesizing them using deposition techniques. Nevertheless, because here we were interested in understanding beneficial feature for MgB2 superconductivity, we picked two of these hypothetical systems, and particularly we looked at magnesium boron, which is the sister compound of lithium boron, and also we looked at lithium MgB2, this compound here, which is as you can see, it's a bridge between lithium boron and MgB, and also was the smallest predicted structure in our calculation. This configuration have many more atoms in the unit cell, and we did not investigate them at this point. Here I'm showing the band structure of these two compounds. So compared to lithium boron in magnesium diboride, the interlayer band, the NFE band, is slightly shifted up because now the interlayer distance has increased, and there is more space for the electrons to occupy these states, which are in this free interlayer region. On the other hand, we are still having that the sigma bands are whole occupied, and more importantly, right now we have density of states coming from the boron pi states. So we can see both in lithium MgB2, there is a significant contribution that comes from the boron pi states, and also in the case of magnesium diboride. So now, what happened when we look at the coupling? So in the case of both lithium MgB2 and magnesium boride, we found much lower coupling than in lithium boron. In fact, we found a value of 0.46. And this is due to the lack of coupling from this low frequency modes in lithium boron. So indeed, if we, for instance, if we exclude these modes when we estimate lambda, we basically found a similar value of 0.46. So in this case, this mode does have, we found that it has quite a significant contribution to the total lambda. And if we look at the superconducting properties, so we found again that with isotropic values for mu star 0.1, we find value of 7 Kelvin and 8 Kelvin. In fact, if you start mu star 0.2 in an isotropic case, you are going to get 0 Kelvin in this case. And while in the anisotropic case, we find values of 49 Kelvin and 54 Kelvin respectively. So these values are much larger, about 7 to 8 times larger than the isotropic values. And that's something that I guess what I want to point out, that this may be important in this kind of layered materials. Of course, as I said, these systems are not metastable. Sorry, they are not stable, so are very not likely to be found experimentally. And finally, here I am also showing the contribution to lambda coming from the sigma and the pi states. And in this case, because of the way the Fermi surface is distributed, the pi and the nearly free electron states are always coupled together, so it's not easy to disentangle them. But what we can see is that while in lithium boron, there was zero contribution from the pi states, now similarly to MgB2, we have significant coupling that can come from the pi states, and slightly larger coupling again that comes from the sigma states, and slightly larger coupling that comes from the sigma states. So that's a summary of our results. So what we can say that we found that in this layer system, it seems important to go beyond the isotropic formalism and investigate superconducting properties using an isotropic approach, since the discrepancy between the two estimates can be quite large. We have also, as I said, we have also identified that in lithium boron can be, hopefully if somebody will try to now to do experiments and measure the superconducting temperature, that it may have a larger critical temperature that originally was estimated. And as Alexei is going to show in his talk tomorrow, that maybe the compound can be synthesized and found in a larger quantity that previously obtained in his experiments. And just as a last point is that we have found a number of promising superconductors, but all this except lithium boron, they have all been found to be metastable and unlikely to be synthesized with a bulk synthesis method, but maybe there is a chance that they could form with layer deposition techniques. And just happy to take questions. And again, I'm showing here the people that have done the work and the funding provided, as I said, by NSF and the computational resources from Exceed and TAC.